Hello everyone, I'm Karen from MDPI and I will be your host for today. Thank you all for joining our second webinar on electronics entitled Beyond 5G Evolution. If you're interested in submitting your paper to the special issues that are linked to this webinar, please check the webinar's webpage. I would like to remind also everyone that this webinar is recorded. The recording will be made available as soon as possible and will be posted on the webinar's webpage. The webinar is also being live streamed on MDPI's YouTube channel, Cypher Room. Hello to those of you watching us on there. Furthermore, certificates of attendance are available up on request to electronics.webinar@mdpi.com. We can only prepare certificates for those of you registered and watching on Zoom, not on YouTube. Thank you very much, Professor Dr. Carlos Jesús Bernardos Cano, for chairing this webinar. Dr. Carlos Jesús Bernardos Cano received a telecommunication engineering degree in 2003 and a PhD in telematics in 2006, both from the University Carlos III of Madrid, where he worked as a research and teaching assistant from 2003 to 2008, and since then he has worked as an associate professor. We are having 3 presentations today, followed by a Q&A moderated by the chair. Our speakers today will be Dr. Ömer Bulakci, Senior Research Engineer at Nokia Bell's Lab, Munich, Germany, Dr. Alain Mourad, the Director of Engineering R&D at Interdigital Labs in London, and Dr. Josep Mangues-Bafalluy, Senior Researcher and the Head of the Communication Networks Division, Telecommunications Technological Center of Catalonia. I would like to thank all of you in the name of MDPI for accepting to give a presentation today. If you have any questions, please feel free to post them in the Q&A box at the bottom of your screen. And now it's time that I hand over the floor to Professor Dr. Carlos Jesús Bernardos Cano. Thank you very much for your participation and enjoy.
Thank you very much, Karen, for the nice introduction. Welcome everybody to this webinar that we are organizing in cooperation with 5Growth, 5G Dive, and Empower projects. This webinar is called Beyond 5G Evolution. And basically what we will do, the agenda, as you already perfectly introduced, we will have 3 talks from our 3 speakers, from Ömer Bulakci, from Alain Mourad, and from Josep Mangues, focusing on different aspects on beyond 5G or 6G technologies. So I will try to be very brief to leave room for the speakers, who are the important guys here for doing the presentations. But just a bit of a kind of motivation scope for this webinar and for the special issue that we are organizing. Basically, standardization in 5G is still ongoing. So 5G became a reality that we can already benefit from, but still there are many things that are still being standardized and deployed, and it will take some time to really get 5G on our life as we expect to get it in different fronts. But at the same time, there are already features that are being identified or associated with the evolution of 5G, what is called beyond 5G, and that will end up being 6G some point in time. So the idea of this webinar is basically to get the different ideas or different views on some of these beyond 5G or 6G topics from different angles, from different scopes. And for that, we are very lucky to have these 3 speakers with us today. And without any additional delay, I think I would like to leave the floor to our first speaker, Ömer Bulakci from Nokia Bell Labs. So Ömer, the floor is yours.
Yeah, thank you very much, Jesus, for the introduction. And so compared to the other the presentations that will follow up after my talk, this talk would have kind of maybe a unique, let's say, approach. So here we will be mainly talking about our working group from the 5G PVP, this is the 5G architecture working group. And we will basically introduce how we operate and how we maintained, let's say, a consolidated view on the 5G system, 5G architecture in the past, and how we would basically exploit this way of working toward the beyond 5G, 6G system, And I will give you some examples of the mode of operation, and then give you that you can have some feeling on the way of handling and what you may expect, let's say, in the near future from our working group. So I had the opportunity to have to pursue the role of working group vice chairman since 2017, and let's start. Okay, so the scope of the working group. So we are one of the working groups as part of the 5G PVP initiative, and we aim to bring the 5G PVP projects together to attain a European view, not only on the overall architecture, but also the specific aspects of the network domains. So of course, there are quite some projects in the 5G PVP, and then they are working on certain technological aspects, but the 5G PVP architecture working group brings the projects, and then we work on a consolidated view and on the technical directions, but with a particular focus on the architecture design. So, and as an outcome of this work, we publish white papers in the form of architecture white papers. We started the work quite early with the beginning of the 5G PVP framework in 2015. And then we published basically our first paper in June 2016, where we mainly focused on the novel trends and the key architecture enablers for the 5G vision. So this has some kind of analogy that we are doing now for beyond 5G and 6G system. And this were based on the outcome of the phase 1 projects. Of course, as the phase 1 projects were being finalized and so on, we worked on a second version of the white paper, and that focused on the key architectural findings and overall architecture definition. So this was in January 2018. Lately, with the second phase of the 5G PPP, the projects have, based on the fundamentals that was established for the first phase of the 5G projects and release 15 of the TGP projects, for the work on the enhancements of the architecture and how different verticals may be supported. So in the latest version of our white paper, version 3, that we released for the public consultation, we worked on the architectural enhancements and what we call the verticals enabled architecture. And as you see here, just to give you the feeling that in this time for the version 3, all the projects but one were participating in our working group, and from the phase 2 side, and also all the available projects from the phase 3. Only one project was missing because they were mainly focused on physical layer aspects, but this shows that we really provide a consolidated view on the architecture design. And I'm also happy to mention that for instance, if you look into the second version of our white paper, this was #1 in the top downloads on the 5G PVP page. So because we don't want to, of course, just only have a consolidated view in the European side, we would like to also reach to establish a global footprint. That's the reason also of the public consultation. So we, just to give some examples on the latest version of the white paper, version 3. Here we had the chapters on the overall architecture as well as the specific network domains that we consolidated from different projects. So we provided this version, we published the version at the UCNC with a workshop, a 5G architecture international workshop on 5G architecture. And that time it was also open for public consultation. So all the comments, let's say, we reviewed not only from the workshop or on the website. So we took these comments into account, and then we further shaped up the white paper. So the latest version is from February 2020. And I'm also happy to mention that also the third version of the white paper, the statistics are not yet released, is still #1 in the top downloads from the 5G PPP. So as said, as an example here, so we consolidated the view from different projects, and we established such a big picture of the overall system architecture. This is the 5G enhanced overall system architecture. We look into the resource and functional level, network level, as well as the service level, how to ensure the service requirements with the service lifecycle management loop. And the network slicing, this is a verticals focused work. So the network slicing has been one fundamental component of the work. So where the functional replacements can be optimized according to the needs of the tenants and the slices. As you see, also we looked into the different types of access, like the satellite access, and also as programmability is one key element of the 5G and the future systems, how the orchestration can be done on per network level, also end to end. So if we have a look to some indicative list of enablers for the vertical support in the architecture work. So network slicing is one, let's say, a critical enabler in the 5G system, and will continue also for the beyond 5G system, where we are hosting multiple end-to-end logical networks on the same common infrastructure, physical infrastructure. And here the key point is not only fulfilling the service requirements, but also assuring the SLAs, the service level agreements between the tenants, the network, the slice customers, and the slice providers, such as the mobile network operators. The multi-access edge computing, so certain services that can be also part of the slices, that we wouldn't have the latency, strict latency requirements. And when we capitalize on the virtualization, the virtual network functions can be further pushed to the edge clouds. This can be enabled by the multi-access edge computing. Such services can be like the vehicle-to-X services, like the cooperative perception could be one example for this. Service-based architecture. We know that in the legacy networks, in the 4G networks, the functions are interworking on rather rigid interfaces, reference points. So with the 5G era, the network functions can be attached to what we call the service-based interface, and any network function or the service of a network function can be easily introduced to the system. So such service-based architecture principle has been applied to the core network and also recently to the management plane, and this provides this flexibility that we are seeking. So functional run split on the radio access side, there were different considerations on the functional split, and the higher layer split has been agreed, where the split is between the central unit and distributed unit. For the control plane and user plane functions can also be split. So that means that the central unit can be virtualized, and this also enables easy scaling also on the run side. Smart network management, when we introduce such multiple network slices, then we, at the same time as we gain flexibility, but we also increase the complexity. So that's why the network management needs to be cognitive, needs to be smart, where the slices can be easily introduced and the slice lifecycle management can be maintained. And when the slice is no more needed, so it can be released. And we also see that both in the management and the core network, that the data, of course, is on the processing of the data has been increasingly important, and then the new analytics functions are introduced both in the core network and also in the management plane. Security should be handled from an end-to-end perspective, so not on the device side, on the user domain security, the network access security, also when we have the service-based architecture, the SPA domain security. So this is an important element, and also there could be tailored solutions such as for industrial IoT slices. So location services, high accuracy and low latency positioning is an important element where new mechanisms have been introduced. This is not only for outdoor, but also for indoor, that can provide location-aware data access. So these are some examples from the architectural perspective. Of course, in the 5G era, there have been quite some enhancements on the lower layers, also such as the flexible air interface, so beam-based communications, the flexible quality of service, flow-based quality of service enforcement has been introduced, and new types of access like the satellite integration has been also introduced. All these are, of course, enabled by network virtualization. So the standardization, the progress has been rapid. So we have, especially with the first phase 1 of the 5G projects, along with there was the release 15. So release 15 and release 16 is where, let's say, they provided the foundation of the 5G system with a focus on eMBB and URLSC extensions, reliable and low latency communications. With release 17, we see further extensions to NR Lite, so support for the massive sensors, massive IoT. And we have also, as mentioned in the previous slide, that analytics has been powering the 5G networks and application of the 5G on the higher layers, as well as in the different access types like the satellites. So release 17 has started, for instance, recently in the run side in August, But of course, there is already a planning for the next release of 5G in 3GPP, and there is actually an excellent opportunity for another webinar if you'd like to see for the opportunities in release 18, some extensions, modifications for industry verticals, that you can attend this webinar as well. All right, so the work, let's say we started, I will show you later, in the working group architecture recently in October. So the projects are still working on their mechanisms. So this is just some, let's say, some teaser for beyond 5G, let's say 6G system that is coming from Nokia Bell Labs colleagues. So some for the enabling foundation for the 6G system. So 6G should unify the experiences, what we call between the physical world, digital world, and the biological world. So it's not only about providing the connectivity among these worlds, but also it's like a synchronization between different worlds. So it should be more like an immersive experience from the user side. So ubiquitous, so what are some enablers for this, or some drivers for such system? So on one hand, we have the ubiquitous compute in a sense, and so as the connectivity becomes can provide high level of data throughput and so on, and then there are new applications, high definition video and so on, or maybe uncompressed data being provided to the devices. So then the computational resources can be moved to the other parts of the network, like to the edge or to the edge of the network, and or even that means the computational capabilities of the devices can reduce, but the computational capacity in the other parts of the network, even maybe the near devices, can be utilized, and with this increased capability or capacity on the connectivities, so we can still fulfill the requirements of the new types of applications. So with the interactions with the digital world and in the physical world, the precision sensing and actuation becomes more and more important. So it's not only about creating the digital world maybe on the go, but also tweaking the digital world from the physical world, and where the sensor capabilities become more and more important. So I think there was one study from IBM side, the knowledge, the information doubles every year, and then this will be even like more exponential in the future, and as the 6G is targeting beyond 2030. So the processing of the knowledge by us, by the humans, would be extremely difficult. And that's why we need to introduce knowledge systems that can take into account such increase of the data, so increase of know-how that can provide planning and prediction for our behalf. And this knowledge system, the knowledge that introduced by the system, can be intuitively provided to the humans by new types of human-machine interfaces. All right, so what are, of course, when we all talk about the beyond 5G and 6G, we always talk about the requirements that can be introduced by the new system. So from the devices, so just some examples here. On the device side, we are talking about further reducing the energy consumption of the devices, so making the devices simpler, and what you call about ubiquitous compute. The computational processing can be done in the other network elements. So sub networks in the sense that the endpoints in the network can be specialized networks. It can be like this as in my background, the swarm of the drones. And we talk about the intuitive interfaces that the digital world and the physical world can be really in sync. And also not only the digital world and physical world, also we can think about and subnetwork be on the robots, industrial robots, are on the body, like on the humans ourselves, like the body area networks. So further increase of capacity above 100 gigabit per second can be envisioned, but maybe more interestingly would be that this should be also provided at the edge. Further improvement on the latency side and reliability side, so to enable new applications like sub 1 millisecond, like 0.1 millisecond or 9/9 of reliability. The coverage should be, as mentioned, also in throughput capacity should be global. So number of devices can be like on the order of 10 million devices per square kilometer, and there could be a new approach to the platform and then services. So that I will touch upon this point in the next slides. So further improvement of the precision accuracy for new, let's say, verticals of industrial communications that we talked about localization in the previous slide, and adaptability, or not in terms of only the configuration parameters, but maybe on the also architecture side that I will touch upon this in the next slides, where like when we look into today's networks, so self-organizing networks, we see that like you observe the network, you collect the data from the network, and then we can tweak like the handover parameters, mobility parameters, and so on, right? What if with the rise of the AI and ML, so we can also adapt the architecture based on the requirements or the changing requirements of the users, and to improve the user experience and so on. So this could be also a next step for beyond 5G, 6G system. So some architectural themes here. So we talked about the subnetwork. So here the endpoint can be a network, so it can be like a body area network here, and that there are the sensors that can communicate each other on the body. So that could be some extensions of what I talk about, the knowledge system, that how we can consume the knowledge with the help of the devices. So this could be also like on the, not only on the humans, but on the robots. That think about like an industrial robot where when we replace wires with the wireless communication, so that we can introduce like tool sets for different operations, and the tool set and the rest of the the control mechanisms can communicate wirelessly also on the robots. So it's kind of like a sub-specialized sub-network also on the robot side. So this also correlates with the cell-free mesh. So if we introduce the side link communication, for the enhancements of the side link communication can be expected. So we introduced like small cells also in the 5G, like the integrated access and backhaul. So one device can reach the network on multiple routes, and this can provide the resiliency that we require if something happens with the blockage happens on one link, and then we can also use it to improve the capacity. As in my background, for instance, the swarm of the drones, they can also establish a mesh network. So for instance, when there is emergency case in part of the network, so that the multiple drones can go there and analyze the network, analyze what the problem is. And so these the drones, when going to this accident area, so they can communicate in a mesh network. So hyper-specialized slicing, of course, the fundamentals of the slicing we have already established in the 5G era, where the core network is fully cloudified, and the functions can be made slice-specific, like the session management function or user plane function. So with the hyper-specialized slicing, we are talking about deeper slicing that can go deeper into the run. Not only in the central unit that the user plane parts can be made slice specific, but also lower layer functions can also be made slice specific. This is what we refer as the hyper specialized slicing. So for the run-con convergence, so the virtualization, we can expect that it to be on 5G, 6G virtualization goes deeper on the run side. So not only in the central unit that I discussed beforehand, but it can be also in the distributed units, also for lower layer functions. So that means that for lower layer functions, we can also make them slice specific. And then as we apply also virtual network functions in the run, so they can be basically deployed on the same cloud, so the cloud, so edge clouds, as an example, and then the core network functions can be moved closer to the cloud and to the edge cloud, and then we can expect a tighter interworking between the radio access functions and the core network functions. So this is considered under the run core convergence. Okay, so this was some kind of like a teaser, let's say, for the Beyond 5G 6G system. Of course, we just restarted the work in the architecture working group. That means that whenever we publish a new white paper, as we have seen some examples on the latest version of the white paper, we give certain time to the project so they can progress on their work. And afterwards, basically, with the new projects, we restart the work. So it's kind of like a dormant phase between the latest white paper and then when we restart the work. So we restarted the work in October 2020, so it is very recent. And we started including the new 5G projects that are, if you go to the 5G webpage, you can see some details on those, and that ICT 17, 18, 19, like 5G Growth is an ICT 19 project, is a co-organizer of this webinar today, and ICT 20 projects. As an example here, the ICT 20 projects were particularly relevant for our webinar today for Beyond 5G and 6G systems, focusing on the 5G long-term evolution, so on the long-term vision of these projects. So we will basically go toward the findings of the projects from the ICT 20. And the last but not the least, so new projects from ICT 52, they're coming next year, so they will kick off next year. They have a particular focus on the Beyond 5G, 6G system. To set up the foundation of the 5G, Beyond 5G, 6G system, there will be a flagship project and complementary, smaller, more focused projects. So these projects will kick off in January 2021. So we will also integrate those projects with the existing ones. And we will, as we did in the past, basically we will look into the use cases, the requirements set for Beyond 5G, 6G system. And this a bit has an analogy with the first version of the white paper. And then we can expect that we can introduce a white paper on this on the scope in fall 2021. So I can say that stay tuned and monitor us and possibly some workshops that we can also organize in UCNC to show the status of our work. So stay tuned and thank you for your attention.
Thank you very much. There are some questions. I don't know, Ömer, you can see them. There is one question that is basically asking a general question about how 5GPP relate to 3GPP.
Yes.
So,
yeah, sometimes like you see that 5GPP has 3 Ps, and sometimes people use 3GPP, and just kidding, of course, in terms of the names. It is like this. So 5GPP projects, these are research projects, of course. I mean, the scope of the 5GPP projects can extend beyond the current release of 3GPP. So the 3GPP, they are organized in terms of releases. So you identify certain study items and work items, and you only focus on those study items or work items. And what we see, for instance, take an example like in the phase 1 projects of the 5GPP, they not only contributed to the release 15, but also although they're in parallel to release 15, for certain topics from the 5GP projects, they were also relevant for release 16 and even for release 17. So the projects, they have longer scope compared to the 3GPP, and that is of course the research, depending on the calls. And at the same time, when there are the ongoing releases of 3GPP, the projects also contribute. So that's why, like when I showed the third version of the white paper, there's a section about the standardization impact. So if you go to the white paper, it's a public, of course, white paper, and then you can see how projects contributed to the standardization developing organization. So it's not only 3GPP, of course. There are quite some other standardization standards developing organizations like ETSI, NFV, ETSI, ZSM. So the 5G projects, PP projects also impact such STOs, not only 3GPP, but of course 3GPP is a fundamental, let's say, medium for contributing the project concepts to the standards.
Okay, so I will be not selecting some of the questions. So there is a question about how, if 5G will use SDN technology or not. This is again a very open question, but maybe I don't know if you wanna take that one.
You refer to Alain or should
No,
we?
to you, Ömer.
Okay, yeah. Yeah, I think what we see as a trend is the virtualization. I mean, further goes even deeper and deeper. So, and then, I think that this will be still relevant, of course, in the 6G era. So, because you see that, of course, every time when we go into a new generation, a disruption is expected and so on, but we also capitalize on what we have achieved in the previous generations. So for instance, in 4G, we had OFDM, let's say in 5G, we further used OFDM, but of course we enhanced the air interface. So we further exploited the flexibility offered by OFDM. So I think, so we can still expect that the key technologies will further evolve toward the beyond 5G and 6G era, like what we call like deep slicing, hyper specialized slicing.
well, there are also some questions regarding the requirements of the 9 nines and the zero energy. So briefly, maybe you can also address those questions, like where these 9 nines come from, reliability number come from, and also about the zero energy.
Yes, so basically, like we talk about the requirements. I think we are talking about a system that will be deployed after 10 years, right? 2030 and so on. I think we should be, and even like this 3 nines or like 6 nines are in the scope of the like 5G or future releases of the 5G. So we shouldn't, let's say, limit us in terms of what we know today in terms of the applications, but that can be achieved, that can enable new types of applications in the era of 2030. And also, like, like when if you look into the industrial IoT applications, so you will see that there are quite some strict requirements, but that are achieved by the wired connection between the control element and the end device. So if you further would like to change such kind of wired communications into the wireless communications with this high requirement on the synchronization, I think we should further work, enhance the requirements that we have set for the 5G system. But of course, like it is always this development of the new generations. They are not based on what we know today, but they should enable new types of applications. So that's why we always see new requirements that are emerging for the new generation. So the zero energy thing is, of course, what we say is zero means, of course, not literally in the sense that we are approaching to such levels. So we would like to reduce the energy consumption on the devices. So just take an example about the virtual reality or augmented reality devices today. So today, basically, what we do, most of the computational processing is done in the end devices, right? So if we can basically send uncompressed data to the devices and handle most of the computational processing on the network side. So what we can reduce substantially the requirements on the computational resources and energy on the end devices. So that's why this 6G beyond 5G system can provide such an enabler. So having such kind of low energy consuming devices. That's I think what's meant behind that.
Okay, and I think that we can take as last question. The one about will the 6G spectrum be different from 5G?
Yeah, I think the other colleagues will further touch upon this question on their talks, perhaps. So like whenever you're talking about the new generation, you want to see how the spectrum needs will change. So what we are available on the below 100 gigahertz, and then we know that above 100 gigahertz, like sub 1 terahertz, there will be more and more spectrum available, and then we are talking about more than 100 gigabit per second, maybe some specialized sub-networks at the endpoints and so on. So definitely, I think we can consider different spectrum allocations for the 6G system. And having said this, the coverage is always an important aspect of the new generation. Even like if you look into the 5G, so there will be like refarming, the reuse of the existing spectrum. So whenever, let's say, more and more devices become available, so then you can reform the existing spectrum and you can make use of the new, more flexible, let's say, area interface in the existing spectrum. That is actually, I think, it's kind of like business as usual, so to say, to look into the new spectrum as well as to utilize the existing spectrum whenever there is a good penetration of new devices available.
Okay, thank you very much, Ömer. So that's very good. And I think we can now move on to the next presentation from Alain Mourad. Please, Alain.
Thank you, Carlos. Can you see my screen? Or most likely not. Here we go. So thank you very much indeed, Carlos. So my presentation today is on the path to 6G. Disable the slideshow mode. And we'll try actually to give you a bit of insights on the target capabilities and technology trends. So this effort has been undertaken in the scope of the Horizon 2020 Empower project that's aiming at developing a technology roadmap for beyond 5G for Europe, but also jointly with the United States, USA. So first of all, I will try to give you 5 mega trends that are underpinning the path to 6G. 2 market trends and 3 technology trends. So the first market trend is indeed this stakeholders race for 6G research leadership that we see. Second market trend is this momentum that's gathering for the support of more and more verticals. The first technology trend is on the rise of data-driven networks with artificial intelligence and machine learning. Second technology trend or mega trend is on this widespread virtualization and disaggregation across all domains of the network, so core, transport, and radio access network as well. And the third mega trend is on the new spectrum and new regulation that we see happening. So you will appreciate actually in this quadrant chart on the left, the impact of these mega trends in terms of the timing, short term, medium term, long term, but also the degree of certainty from low, medium to high. So let's dig down a bit on each of these mega trends, starting with this race for 6G research leadership. So the key insight here indeed is that such a race is already on. So we see multi-billion US dollars or euros, multi-year government programs already launching from multiple countries and multiple regions around the world. But we also see key stakeholders, industry stakeholders announcing their 6G roadmaps, like the Docomos, the Ericsson, the Nokia, the InterDigital, right? And they are launching the 6G labs as well. So if you take some examples here, actually, on the left-hand side, you see in this on this slide, there's this Horizon Europe program that's succeeding with the Horizon 2020. So this is the next 7 years framework program, which includes the smart networks and services kind of framework activity that will be underpinning 6G. But there's also this 6G flagship activity that started in Finland a couple of years ago. In the States, we see a number of activities where the USA is trying to assert their beyond 5G, 6G research leadership. For example, this FCC experimental framework program for frequencies above 95 gigahertz, the ORAN bill, and most recently, the announcement by ATIS on the Next Generation Wireless Alliance. And similarly to the 6G flagship in Europe, there has been recently the launch of 6G Symposium in the United States. Also in Asia, China, Japan, and South Korea, we see a number of initiatives already announced around 6G. And perhaps some are quite ambitious, like the one in South Korea, already aiming at 6G trials by 2026, so within like 6 years' time. So what does it mean, actually, all this insight about the race for 6G research leadership? So what does it mean to us? And by us, I mean we, the industry R&D. Obviously, such a race kind of drives us or puts the onus on us to drive harmonization efforts on a unified vision, 2030 vision, in the international fora, for example, like ITUR, GSMA, and NGMN, so that we try actually to align as much as possible and agree globally agreed requirements that will drive actually the specification of 6G. Moving next to the second mega trend on the support of more verticals. So the key insight here is indeed that industry verticals and industry applications will indeed remain the biggest growth area for wireless communication. And they will also be a major driver in the evolution of 5G. So we clearly see this happening today, actually, with a number of alliances. For example, the 5G Alliance for Connected Industries and Automation, so 5G ASIA, led out of Europe, but also its peer alliance called 5G DNA, Deterministic Networking Alliance, led out of China. So we see these fora already actually working with the 3GPP and pushing extreme use cases with extreme requirements that will push the envelope of the current 3GPP release 16 and 17 specifications especially in terms of end-to-end latency and reliability. So we already see requirement or use cases for requirements pushing the latency down to the below 1 millisecond and reliability up to the 8 nines, especially for like use cases around motion control. So what is crystal clear here in terms of impact, that 5G has only started actually to accommodate the requirements of the verticals, and we'll see beyond 5G and 6G developing even further and pushing these, supporting more and more these requirements as we go forward. The first technology trend, the mega trend, is on this rise of data-driven networks with AI/ML. So what's clear as an insight here is that AI/ML, they already, these tools already penetrated the web technology, the network technology, and the chip technology. And this trend will only continue actually as these tools and algorithms mature and more data becomes available. So I just depicted a few examples there on the left-hand side of the slide. So we see some announcements on AI automation already being applied to the network management, for example, with Ericsson. We already see AI/ML heavily deployed in solutions, in the web technology solutions like RankBrain from Google. And what's actually quite striking is the booming sector of AI chips. So there's already a forecast actually that such a sector, the AI chip sector, will be, the market size is going to multiply by 10 times what it is today. So today is estimated about $7–8 billion. And it's only by 2025 that such a market is anticipated to reach $92 billion. And we clearly see all major actors playing in this space. You know, the Google, the Apple, the NVIDIA, the Qualcomm, the Samsung, the IBM, all these major players. So what does it mean for us again in terms of impact? That AI/ML clearly will have the potential to disrupt the design of our future wireless networks and devices. So we'll see disruption of such a technology in the core network, in the access network, in the edge, but also on the devices themselves. So moving next to the mega trend on virtualization disaggregation. I mean, virtualization is already at the core, is already a major feature in 5G and also on the edge. But we clearly see the momentum gathering for deploying virtualization into the radio access network as well. And that's evident actually with initiatives like ORAN, Open RAN, software-defined RAN. So clearly what this means actually is the trend around virtualization and disaggregation of the network is going to be disruptive, not only in terms of technology, but also in terms of business aspects, intellectual property aspects, regulatory aspects. And and even if we overcome these challenges soon, it might take actually until 6G before, as we say, the full breadth and depth of possibilities here are realized for virtualization and disaggregation. So now that I kind of briefly run through these mega trends, so I will try to expose some of these capabilities that we see 6G targeting and the technology trends to meet or fulfill these capabilities. So first of all, before we dive actually on these target capabilities and technology trends, so this is a slide here where we show key stakeholders that will be driving the agenda of 6G. And we see the way this is presented here on the slide is from the most exploratory on top, like programs like Horizon Europe program, and moving all the way down to the heartbeat of what's going to be 6G in terms of specification, and that's actually the 3GPP. Right? So here on this slide, we present the Horizon 2020 on top as the research program. It's expected or anticipated 3 cycles: exploratory research, proof of concepting, and pilots and trials. But then moving to less exploratory kind of fora, but still focusing on technology trends like ITUT, with its current machine learning for 5G and beyond, Network 2030, but also other activities around artificial intelligence, quantum communication, and so on. And indeed, where we need to also put some focus here is on ITUR, which already started this year, early in this year, in February 2020. They already started actually developing the vision for what's coming up next. That's IMT 2030 and the technology trends. And we anticipate the same cycle to repeat after this vision technology trends. We'll see requirements, and then following the specification of 6G in standard organization like 3GPP, obviously, we anticipate that ITUR will develop evaluation methodology, do evaluation, and issue recommendations of what IMT 2030 is going to be. Clearly, ETSI is already active in a number of areas that will be at the heart of 6G system, including millimeter wave transmission above 100 gigahertz, edge compute, network intelligence, zero-touch management, and so on. And the specification groups like IETF, IEEE, and 3GPP, they are already embracing actually some of these new requirements. So we see, for example, IETF is already developing further the transport technology for immersive multimedia. IETF is also working on applying or augmenting the deterministic networking for application to the wireless domain with reliability and availability for wireless, also bringing automation and AI to network management and so on. Wi-Fi is still very active, developing the Wi-Fi 7 now, and launching a number of study items around sensing, but also sub-terahertz. And that's going to continue actually for the medium term and long term, and that will drive obviously the agenda on 6G as well. And as for the 3GPP, as we all know, it's already working with release 17 and 18 in terms of some evolution of the 5G release 16. And then we see in the midterm some form of advanced 5G Advanced Pro. Only from 2026 that we anticipate actually a potential breakaway from the backward compatibility of 5G. So with releases 2021 onwards to see the first specification of a non-backward compatible 6G specification. So this is the kind of the forums, and now we'll just present as briefly as possible on my side, and for the sake of time, the wireless capabilities. So the target capabilities on the wireless side and the technology trends that will follow, and we'll do the same exercise next for the network capabilities, not only the wireless interface. So what we see here, the way this slide is structured. So on the left-hand side, we see the different capabilities, or if you like to call them requirements. On the green is what actually the values or the target figures for these requirements in the IMT 2020. And then in blue, it shows actually as a direction of travel, what's the ultimate goal for each of these capabilities in IMT 2030. So I'm not going to go on each of these KPIs, but just to pick a few. If we take, for example, spectrum. So spectrum today, officially and formally under IMT 2020 for 5G, it's capped up to 100 gigahertz, right? So that's the definition of IMT 2020. So clearly we see this cap being removed as we look at IMT 2030, and that carrier frequencies as high as 300 gigahertz are likely to be supported. And as this frequency or the spectrum goes significantly up compared to IMT 2020, obviously the bandwidth is going to also go up as well, right? So the bandwidth today, if we take the bandwidth today in IMT 2020 for the high frequencies, so it's about 1 gigahertz, right? The single channel bandwidth. So this is anticipated as we move up to the 300 gigahertz kind of range. The single channel bandwidth would be above 10 gigahertz. So that's a factor of 10 times. So if obviously the peak data rate will also follow the user data rate as well. And it's noticeable here actually that compared to IMT 2020 user data rates, which are around 100 megabit per second downlink and 50 megabit per second uplink. So we see these this user data rate reaching gigabit per second downlink and uplink. And that's in particular for multi-sensory extreme reality and volumetric media streaming kind of use cases or gaming use cases. The latency is going to go down as it is forecasted, both in the user plane and the control plane, reaching lows in the user plane below the 0.5 millisecond and the control plane below 5 millisecond. And that's mainly for use cases around connected industries, autonomous vehicles, and tactile use cases. Reliability from the 5 nines today up to 8 nines, same for industry verticals use cases. connection density multiplying by a factor of 10, similar to what Ömer just highlighted or hinted about in his presentation earlier. So we see this going up to 10 devices per square meter, or equivalent of 10 million devices per square kilometer. And that's mainly for use cases around ultramassive sensor networks. Energy efficiency, obviously, even though it is qualitative today in IMT 2020, we clearly see the green agenda weighing significantly on the requirements for 6G. And we see this energy efficiency being a major capability that need to be boosted both on the terminal side and on the network infrastructure as well. Positioning accuracy, this was not and is not actually a capability, official capability in the IMT 2020 as such, even though 3GPP attempted to achieve some positioning accuracy KPIs. But we see this increasingly of major interest to industry verticals, and the 6G or beyond 5G trying to achieve centimeter level positioning accuracy, both indoor and outdoor. Mobility, again, will be kind of at least double beyond the 500 km/h today to about 1,000 km/h. And that's mainly actually for the support of flying objects like airplanes and high altitude platforms. Right, so with this, I'll move to the wireless technologies. So the wireless technologies are those enabling technologies that will help us meet the capabilities I just presented earlier. So here we see technologies around the spectrum, the massive MIMO, waveforms, coding and modulation, multi-connectivity, and positioning technology, just to list a few. And again, the status is presented in green, the status today of these technologies, and we present next the roadmap in terms of short term, medium term, and long term. So if I pick again the spectrum side here, so today, for example, in the 3GPP release 16, we still, we have some new radio specifications for frequencies up to 52 gigahertz. Right, or 52.6 gigahertz. But we also see in the backhaul, there are solutions in the backhaul that go as high as 100 gigahertz. As we look at the short-term evolution of the spectrum technology, so we see actually already enhancements reaching the 100 gig. So we will stay actually below the 100 gig in terms of inner access. And that's actually, for example, already happening in the release 17 and 18 of 3GPP, where they are trying to go above 71 gigahertz, right? But also in ETSI, MWT, ISG, they are trying to explore backhaul spectrum solutions above 100 gigahertz. And if you look at the midterm, so this is when we anticipate actually that this cap of 100 gig will be effectively lifted. And we see the first new design above 100 gigahertz and some form of AI-aided spectrum management, as well as some form of joint sensing and communication. So all this in the kind of spectrum technology. And in terms of long term for that technology track, so we see when we actually reach high frequencies, very high frequencies in the 300 gigahertz. So this is when we see actually the opportunity for a very disruptive design, perhaps breaking away from the incremental evolution design in the 100 gig and the 70 gig, right? And perhaps with opportunities as well for a full integration between sensing and communication technologies, right? So if I pick actually massive MIMO as another technology, enabling technology, so there are already enhancements being developed today actually for beamforming at high frequencies, but also for support of multi-users scenarios. So this is going to continue until 2023 kind of time frame, the short time frame. And as we look actually to the medium term, so this is when we see really large antenna arrays and super high directivity at higher frequencies, but also significant boost to the distributed and coordinated multi-point schemes, right? And as we envision the long term of massive MIMO, so this is where we see ambitious schemes around holographic MIMO, 10, 24 or more antenna elements, reconfigurable intelligent surfaces, AI-aided ultra-massive MIMO schemes. So quite ambitious research trends. So I'm not going to actually go again through each one of these technologies, only for the sake of time. So all this is available for everybody on the Empower website, but also in some of the publications we have. And I'm sure these slides are going to be available. But let's maybe pick one more actually here. So for example, the multi-connectivity. So the multi-connectivity framework today is very much around dual connectivity in the 3GPP and some kind of dual access between 3GPP and Wi-Fi. It's very much a clear trend in the short term that we see more and more focus on unlicensed and the integration of licensed and unlicensed. So even 3GPP unlicensed. Right, but also some form of integration, enhancement of the integration between the access and the backhaul as well. Right, so these are like the short-term kind of trends, and as we look to the medium and long term, so this is where we see the full-fledged potential actually of a multi-access based multi-connectivity, including licensed and unlicensed, terrestrial and non-terrestrial, wireless and optical wireless, and all aided by some form of smart multi-access management based on AI. Right, so I'm gonna just leave it here for the wireless technologies, enabling the capabilities I mentioned earlier. So we'll do the same exercise, and we did the same exercise in this Empower project on network capabilities. So here the network capabilities are a little bit softer than the capabilities on the wireless interface side. So here we talk about capabilities around automation, flexibility, determinism and resiliency, energy consumption, coverage, security and trust. And in the very same way I presented earlier the wireless capabilities. So there is a state of art today in Network 2020, not IMT 2020, but Network 2020. And then the direction of travel as we go to Network 2030. Right. Again, I'm going to pick a few here. So if we take automation, so it's still to a large extent today the state of art that the network is human operated to a high extent. And the vision actually for that capability moving forward to Network 2030 is that actually that Network 2030 is going to be self-operated to a large extent, where human operators are only required to validate certain decisions. Right? If I pick another one, like the service deployment time, so today in the Network 2020, it's around a few hours to deploy a new service. And this is anticipated to reduce by a factor of 10 going forward, and leveraging in particular slice creation and sensation on the fly kind of technology. If I pick determinism and resiliency, so this is to a large extent today limited to wired network. And clearly we see this going forward extended to support determinism and resiliency in industrial wireless. And that's what I alluded to in my one of the slides before on, for example, IETF already working on applying deterministic networking and reliability availability for wireless and time-sensitive networking. If I pick the coverage side as a capability here, so it's still today very much segregated between terrestrial and satellite. So we see as a capability here the trend to achieve some form of ubiquitous coverage based on the integration of terrestrial and non-terrestrial networks, including both satellites and high altitude platforms. Yeah, so that's on the network capabilities, just to give you a bit of a snapshot of these capabilities we developed. Likewise, we do here for the network technologies, so that will be enabling the KPIs or the capabilities presented just before. So here we have enabling technology around edge native compute, virtualization, slicing, automation, and network AI ML, distributed ledgers, and so on. Again, to pick a few here, if I take edge native compute, so already edge is being integrated today in the 3GPP 5G system, right? And also ETSI is kind of developing some work to bring that, to push the envelope a bit further of edge. So as we look at the short term, 2021, 2023, we expect actually this edge plus 5G integration to continue further. And we see some first forms of enhancements of the distributed edge through microservices kind of framework. And as we look at the midterm, so this is where we see new topics around inter-edge interworking and federation, but also supporting of mobile and power-constrained edge hosts. And as we look at the long term, so this is where we see intelligence supporting the full-fledged of end-to-end edge, cloud, edge, and far edge on the terminal device as well. If I pick, for example, the automation and network AI ML, so today the state of art is still very much around big data based management and the OSS and BSS. So we see in the short term some form of enabling framework of automation in 3GPP, for example, around this network analytics framework, but also some form of non-real-time run management kind of applications. As we look to the midterm, so this is more where we see zero-touch management, small data-based distributed analytics and distributed AI, both for the control and the user planes. And looking to the long term, so this is where we have the promise of a full automation and distribution end-to-end, including on the device itself. So this is just to give you a bit of a taster, actually, of what these network technologies are to meet these capabilities. So I'm going to come to the conclusion for the sake of time as well. So it's clear, actually, that today we are in quite early stages of the rollout of 5G, but we still have a long way to go forward. That said, it is the right time, actually, to ask ourselves what's coming up next. And what's striking indeed, actually, is all these emerging use cases for beyond 5G, 6G, they all look familiar, actually, because these have been promised in 5G. So, what this hides as a truth is indeed that 5G may only be the beginning and opening the door for the support of these use cases. We see extreme requirements coming to push the evolution of wireless, noticeably from industry verticals. And indeed, when looking out to the future, we see actually inflection points happening indeed to make or lead to a 6G system. So with this, I would like to thank you very much and would like to thank or acknowledge the Horizon 2020 Empower project for all the work that have been put into this presentation, as well as the 6G award for the mega trends that have been laid out at the beginning of my presentation. With this, I'll give the floor back to you, Carlos. Thank you.
Thank you very much, Alain, for this very interesting presentation. So if people have questions, please put them on the chat. While we wait maybe to see if there is any question from one question. This Empower initiative, what is the time frame that you guys have? So how long is gonna and yeah, what is your time frame?
Right. So this Empower project started, let's say, late 2018 or beginning 2019. And that's running for 3 years. Now with the COVID-19 pandemic, I think that has been extended a bit further. But clearly in terms of timeline for generating these roadmaps, beyond 5G roadmaps, so we already released the first roadmap that has also been published in the MDPI Electronics special issue on beyond 5G. And the next release of the roadmap is going to be February 2021. And ultimately, that will lead to a final roadmap just on time for ITUR WP5D on the Vision and Transfer IMT 2030 around the end of 2021 or beginning of 2022.
Okay. One maybe not it's not a very technical question, but just a curiosity. What is your opinion on what has been the impact of, now that you mentioned the COVID-19, on the standardization side on beyond 5G plans?
Yeah, honestly, I don't think it's impacting much actually on the let's say the 6G timeline, because as you appreciate, Carlos, and you are one of the experts in standardization activities, right? Especially IETF, right? So all these standard bodies are still, working on some incremental enhancements to their early 5G specifications, right? So they are not much worried or concerned now with the long-term 6G issues, right? So honestly, I don't think the COVID-19 pandemic, hopefully, if it ends, in the next few months, I don't think this has any impact really on the beyond 5G roadmap.
Okay. Thanks a lot, Alain. And I think that we can turn to Josep.
Okay, thank you.
Thank you very much.
Okay.
Okay, Josep. So you have time if you want. We discussed before, but I think you can take the time that you need. Okay.
Okay. Thanks.
Thank you.
Okay, so thanks, Carlos. So what we are presenting here is what is the take of the Phi Growth project, which is a phase 3 5G PPP project on the evolution of network architectures, not just for 5G, but also we believe that some of the things we are doing match exactly what Alain was just explaining and what Ömer also was mentioning before. So we're going to try to give you here some of the tangible things like the pilots and the proof of concepts that we are doing in our labs and in real setups to try to, let's say, hopefully convince you that we are in the right track, right? Five Growth is not an isolated initiative. It inherits results from previous projects, phase 2 and phase 1 also even. So for example, from 5G transformer. And in fact, when we present the examples, you will see that we are reusing and benefiting from work of previous projects, right? By the way, what you see behind me is one of the labs that you will see in action in some of the results. This is called the Extreme Lab of the CTTC. Well, we have another optical one that you will also see in action and interacting also, for example, with other test beds, for example, Fivetonic in Madrid, as you will see in some of the setups. So hopefully I will convince you during this presentation that, as I was saying, we are in the right track and that what we are doing makes sense, not just for 5G networks, but also like towards 6G somehow. At least we are dealing with, and we already have some results that go in the direction that were presented previously. And it's not just architectural work. As you know, in phase 3 projects, we are mostly interested in putting into practice things. Like previous projects were more on the architectural and high-level definition of the architecture and a small-scale proof of concepts. What we are actually doing in Phi Growth is pilots in real setups, right? So that's what we mean with tangible results. And these are our pilots. So in the end, what we design, of course, is a generic network infrastructure that is supposed to serve many different vertical pilots, not just this one, but general ones. And the architecture is designed for that. But of course, in the case of Phi Growth, we are targeting specifically these ones, which are Industry 4.0, for the case, for example, in Novalia, in Bilbao, and Comau in Italy. And then also transportation and energy in Portugal, in the case of EFASEC, right? So we do that by combining, as we were saying, like the real setups in factories and in the harbor of Aveiro, for example, or real substations. This is the part of the pilot, and combining it also with the labs of the partners, like for example, University Charles III and Fivetonic lab and our lab and lab from other partners, right? So you all know about the requirements. They have been explained in previous presentations, and I will not go into that. So we also inherit somehow these requirements, and these are the ones that we are supposed to serve. But in the end, as Alain was explaining and Ömer before, so the trends that we are following here, and the main ones, let's say, there are many more, but let's say the trends that we are following here is this vertical orientation. So we are interested in serving the requirements of a variety of use cases, vertical oriented use cases. This trend of disaggregated network equipment and softwareization, which in the end, in practice, what it means is that you're introducing multiple new interfaces that were not there before. And whenever at the architectural, if you want, at the more technical level, you're introducing an interface This translates at the business level in introducing new stakeholders and so new businesses. So this is something that we will have to deal with also, which come hand in hand with these new stakeholders. As we were saying, this trend of ubiquitous computing brings in practice distribution, like geographic distribution that you will have to handle, but not just, let's say, distribution on the data plane, but also on the control plane, because you cannot assume that all the computing devices that you have will be managed in the same way, right? Since Phi growth, one of the main targets is controlling the network somehow end to end. Like this is also relevant for us in the sense that it introduces heterogeneity that we will have to deal with. But heterogeneity does not come just in the management plane, let's say. It also comes in many different ways, like the requirements from verticals, as we were mentioning, and also the plethora of multiple technologies that we will have to handle and integrate into a single global network that serve a variety of needs, right? So we will have multiple access technologies, we will have multiple transport technologies. So all this is generates. So what's the result of that? It generates a complex network, a really complex network that Phi growth aims to control, which will feature multiple administrative domains. So we will have to interact technically and also administratively with these administrative domains. So this includes, as mentioned before, NPN to PN integration, which is also something that we are tackling in Phi growth. We will have to interact with multiple providers that will provide multiple different components of this architecture. And of course, we will have multiple technology domains to handle, including the RAN and unevolved RAN, in the sense that if you add it to this softwareization trend, I mean, it's even more complex that it is already by default, let's say, right? So this complexity we will also have to handle. And as also mentioned previously, we are also aiming at dynamically adapting to the varying requirements and these varying network conditions and services coming and going. And for that, applying AI/ML seems to be the trend that we are also following in this project, and you will see some example afterwards. So how do we do that? What you see in the middle, this part here, is the stack that we are inheriting from 5G Transformer. This is the baseline architecture that we are leveraging from 5G Transformer, phase 2 project, right? The main building blocks of this architecture are the vertical slicer, service orchestrator, and the resource layer. So basically, the vertical slicer will be the one interacting with the vertical. So it will expose an interface that is understandable by the vertical, so that the vertical can focus on the business logic, let's say, and requesting the services that are understandable and with the components related with the business logic of the specific vertical. So it somehow it abstracts to the vertical all the underlying details that you need to configure and handle so that the vertical can just focus on what it is of interest for them. Then at the bottom, as we were mentioning, we will have to handle the heterogeneity of technologies. So that's why we have another layer in our management stack, which is the resource layer, which will basically aggregate all the different resources, the heterogeneous one, and expose them in a homogeneous way to the service orchestrator, which in this way somehow can forget about the underlying nitty-gritty details of each of the technologies and focus on offering the service and, of course, handling at a high level the resources. Okay, so the service orchestrator will be the one mapping the requirements coming from the top to the underlying network to fulfill these requirements, okay, based on the available resources that are exposed by the resource layer. And not only that, but It will do it by interacting, of course, with a monitoring platform. We had a basic implementation in Transformer also, but now we are further extending not just the monitoring platform, for example, to consider and take decisions more based on vertical-oriented metrics, but also to interact with the AIML platform that we are designing in Phi Growth to take this kind of decisions and enabling all sorts of intelligent decisions at any layer in our management stack. Okay, so additionally, we are also exploring, I mean, as I was mentioning, one of the key things that we are doing is the NPN and PN integration, right? So we are exploring different ways to do that. And this is what these arrows are representing. So we will have other providers in other domains, and there are different ways in which you can interact with different providers, because as we were saying, there are multiple stakeholders, there are multiple kinds of relationships between providers, and we want to like offer a solution for all of them. And this is what this slide is representing. So if we zoom in a bit in the vertical slicer, this should sound familiar to you if you're familiar with the 3GPP specs. We also have our take at it. So the CSMF, or sometimes we refer to it to the VSMF, because it's not just about communication service management function for us, but vertical service management function. This is one way in which we can interact in a federated way, let's say, between multiple domains. And in fact, this is the one that we are using to interact with 5GIF, okay? Then there are other ways in which you can have a multi-domain approach. For example, the one we will use with Vini, we are using with Vini already, in fact, is through this arrow here, which basically makes the VSMF or the CSMF request network slices to the other domain. So by following the NSTs defined by 3GPP, for example. And then we are also having this kind of interaction more at the service orchestrator level, which we call, for example, service federation. You could also do resource federation, which in fact we are also improving. We had some version generated already from Transform, and now we're improving it in Phi Growth. So as you see, we are offering different ways to adapt to the multiple possible interactions and stakeholders and business nature of each of the stakeholders. We are offering multiple options of multi-domain integration. So if we go a bit one by one to the different building blocks of the architecture, so the vertical slicer, of course, there are many more building blocks inside, but let's say, as we were mentioning, this is the VSMF, the vertical service management function, which will be in charge of somehow translating the requirements that are understood and the agreement that the vertical has with the provider of the service, it is translated into a slice request, okay, by this building block. And this slice request in turn, by applying the extensions defined by 3GPP and so on, will in the end will be translated in turn to an NFV network service request, which will be the architectural construct that is handled by the service orchestrator. Okay, so this is the main role of the vertical slicer. Of course, for example, you also have arbitration modules here where you have intelligence and you can decide how to prioritize requests from different vertical service in the same slice and between different slices. That we are also aiming at integrating with AML platform. And in fact, you can take a look at the Transformer YouTube channel and the Growth channel to see demos on this. So this was it for the vertical slicer. Now, if we go to the resource layer, how do we scale this huge heterogeneity of technologies? Then the way we decided to do it is through abstraction, by introducing different layers of abstraction, as we were mentioning. So what you're seeing here, I mean, by the way, you will see references to the papers where we published this work through the presentation in case you're interested in the details. Then basically, the resource layer, which in Transformer was called MTP, but we're also improving, and now we are calling Phi Growth Resource Layer. So the resource layer will take whatever is exposed by the multiple transport technology domains. WIM stands for Wide Area Network Infrastructure Manager. So sort of SDN controller of a big domain, let's say. Vim would be OpenStack, for example. It will aggregate all the resources coming from these different computing and transport domains and will abstract and expose them to the service orchestrator. For example, in this case, we are abstracting, we have this network that is coming from below, where there are 2 POPs represented. And then in this case, we are having 8 nodes, right? So these 8 nodes, from the point of view of the service orchestrator, are abstracted. Let's say it's too detailed because the resource layer provider does not want to show the structure of the network, or for any other reason, or for scalability reasons, for example, as we were mentioning. This is abstracted as a logical link with certain characteristics, in this case, bandwidth and latency. And these resources are the ones based on which the service orchestrator will take decisions for placing, for example, functions, for selecting paths. And then when it comes to the resource layer will be the one responsible for de-abstracting this selection of a logical link and constructing a path through the actual resources that we have. Okay, so this is one way in which you can scale. And in previous projects, even in phase 1 project like 5G cross-call, we went deeper, and below this one, you could have a hierarchy that could also somehow even abstract more the resources, right? So this is one way in which we are handling these scalability issues when you handle this technological heterogeneity, right, through the resource layer. Then, in terms of resource layer, of course, as discussed, I will not go in detail, but basically this matches quite a lot what previous speakers were discussing, right? So we must introduce, for having a resource efficient use of all the resources that we're aggregating, given their complexity, you must go to AML decision making. So for example, to handle anomalies, and these kind of things are improvements that we're introducing to our 5 growth stack. Joint access and backhaul optimizations, as mentioned before, better consideration of the RAN, not just conventional RAN, but also disaggregated RANs, and other sorts of approaches that are being considered for 6G. Let's say for example, this last one, the cell-less architecture, of course, we are not yet there, but we believe that the architectural constructs and the management software that we are designing could enable this kind of approaches. So what about the service orchestrator? So we've seen what the vertical slicer does, what the resource layer does, and why they were designed the way they were designed. And we have a sort of central component in the middle that somehow makes both talk to each other and translates, for example, takes the requirements coming from the vertical service that come from the top, from the vertical slicer, to the resources that are available at the resource layer, right? So, and how is this done? So we have here some building blocks that do the mapping and do the placement. PA stands for placement algorithm. So we will receive a network service request here with a certain structure for the service, a certain number of VNS with requirements at the link level in terms of bandwidth, latency, or whatever. And we will know the available resources from the bottom, and the placement algorithm will be the one selecting the most appropriate spots where you need to deploy each of the VNFs. And then the service orchestrator, since it has an end-to-end view of the service that you want to deploy and also an end-to-end view of the resources available, at least of the abstracted resources that come from the resource layer, is the appropriate place where you can make sure that the requirements are fulfilled. The other nice feature that we embedded in our service orchestrator is that we are capable of integrating core Mano platforms like the well-known core Mano platforms like Cloudify and OSM. You will see an example of how two domains, one of them using Cloudify and another one using OSM, interact. And we also have other building blocks for SLA management, for monitoring management, for configuring, automatically configuring monitoring jobs and gathering data, generating alerts for SLA management. You will see the AIML-based version of these in the last slides. Okay, and we will also talk about these two building blocks in a minute, to talk about how we do service federation. So this is about the service orchestrator. And these are some of the results that we just published, like in July in COMMAC, so that you have an order of magnitude of the instantiation time. So as mentioned by Alain also, this is one of the key KPIs. And this is what we are achieving for the service structure that you see depicted in the slides. So in this case, it's a virtual CDN server. We have two flavors. So one instantiation level, meaning that you only have one cache and still the web server and the origin server, and the big instantiation level, which has two cache servers, for example, because you want to deploy to give support to more end users. Then what you can also observe for these measurements is that the most time-consuming part is the one about resource handling and deployment, right? So by far, the yellow one is the bigger one, which has to do with, in this case, we were deploying virtual machines. So these VNS were deployed in the form of virtual machines, and this is the time it takes to deploy these VNFs, in this case 3 or 4, right? Then the other part is the creation of the intra-pop networks by interacting. In this case, our beam was OpenStack. So this is the other big component. And the rest of the processing is much smaller. The one inside the service orchestrator, the building blocks that I just showed, or the one inside the vertical slicer, and in this case we were using polling, so some time is added by the polling policy. But you see that we are in the order of hundreds of seconds, right? So let's say minutes, which is much lower than what you achieve when you have manual interaction between departments, even inside the same operator, which could take even days in some cases. Then, what about slicing support? What's our take at that? So the important thing here is that in slicing, you have two main ideas that you need to solve. It's not just about offering the service and nothing else, but you need to, the definition of a slice in fact includes the term resource. So a slice is the service that you want to offer and the resources that you need to offer it end to end, right? So you should not forget about these resources, and you need to make sure that you have these resources under control end to end. And the other important thing is that you may have components of this slice that you share with other slices, right? Like in this case, for example, if you see in the right-hand side figure, you see the yellow subnet instance. The yellow one is shared between network slice 3 and network slice 4, right? So this is something that we also need to support. Because, for example, you may want to share the mobile core between different slices offering different services, right? And the same idea comes also not just from NGMN, which is the figure that you see to the right, but also from 3GPP, where in this case you see, for example, the access network that is shared between two different slices, with each having its own core network. The other idea that we used for offering this slicing support is the idea of composite network service. So this idea defined by HCNFV means basically that the network service F, the one you have to the right, is sort of an abstraction that aggregates some internal sub-services and exposes some of the interaction points that this composite service offers, right? So then this architectural construct allows us also to share, for example, a sub-service while or to link new sub-services to one shared service and build a composite service which constitutes our end-to-end slice, right? And if you want to see a demo of this, of what we did, for example, you can go to the YouTube channel, in this case of Transformer, and more updates will come in the growth one. So these are the architectural constructs and the considerations that we make to support the slicing and composite network services while we go to federation, which was also one of the keywords that Alain was mentioning in his slides, to be supported by 2025, I think, or something like that. So we have our take of that. Of course, it's not full-fledged and does not solve all the issues, but we have an operational implementation of Network Service Federation, where basically we are building an end-to-end network service catalog together with other providers. And this is, so let's say there will be a domain which will be the reference one, the one with which a vertical will interact. This network service catalog will come aggregated to this vertical, which will not know the kind of relationships that the provider, the domain, the Phi growth provider has with other peering domains. This is not its concern, but in the end, some part of the service that is requested by the vertical may be deployed in another domain through this common aggregation of services, right? So this is our understanding, in this case, of Network Service Federation. And as I was saying, we are exploiting the concept of composite network services. And we are doing that. This is one of the ways in which we are offering multi-domain, as I mentioned before, at the service orchestrator. Why in this case? Because we have an end-to-end view of what we want to offer, of the NFV service that we are deploying. And not only the service view, but as I was mentioning, when you deploy a slice end-to-end and it spans multiple domains, you also need to make sure that you have control of the resources. So let's say that the reference provider for this vertical will have control of its own local resources and also a partial control of the remote resources, at least to make sure that there are not conflict of identifiers, of VLAN IDs, of IP addresses, and so on. And as you will see, it also allows integrating, as I was mentioning, the way in which we modularize the service orchestrator. It allows integrating Cloudify and OSM, or through wrappers, you could also add other Mano platforms and have service federation. So how was this done? So this is again the service orchestrator. So these were the two modules that we added to our initial implementation at the service orchestrator. This one, the service orchestrator engine parent, is the one handling the composite network service structure and decided what part of the NFV network service is deployed in what provider, for example, so handling the interactions at the service level. And we also have a building block, the composite resource orchestrator, that is the one handling resources. And of course, we defined some interface, which in this case is based on ETSI IFA 13. In fact, the same one we are using here between the vertical slicer and the service orchestrator. And this is what allows us to have inter-provider interaction. Of course, we also took a look at many other specs like IFA 28, IFA 13, but let's say the emphasis there was mostly put on the service handling, and we were interested for the reasons I explained before of handling also and having an end-to-end control of the slice, right, across multiple domains. Of course, each part of each domain will control its own resources, but there should be some sort of coordination. Otherwise, we could not establish the communication. And then there would be some sort of customer domain. The one receiving, for example, the request from the vertical slicer will request the deployment of some subservice to another provider, right? This would be the provider domain. Then let me give you a quick example of that, of what we do. This has been demoed at InfoComm this year, and it was also shown in the final audit. You also have a video of the demo in the Transformer YouTube channel. This is the structure of the composite network service. So what you see here, the blue part is the mobile core plus a server. In this case, it's called eHealth Monitoring Network Service because it receives the vital signs of a user because, for example, it has some cardiac issues and you want to have him under control. Then when there is an emergency, this second service will be automatically deployed and automatically stitched to the initial one. And this one will be the one that is needed to handle the emergency. Okay, so this is the basic idea. And what you will have here, for example, is services related with augmented reality to help the doctors reach the exact spot of the emergency. And in this case, you would also have a mobile network building block to do the local breakout because we're interested to deploy these servers at the edge due to latency constraints. Okay. Then, how does the growth system work? So this is the graphical user interface of the vertical slicer. So in this case, the SAMUR, the Emergency Services of Madrid, would come to this web interface and request the deployment of the monitoring service for a given user. And once it is deployed, and this is the graphical user interface of the service orchestrator, you would see the service is instantiated. This is the structure, and you can see, and we have a graphical user interface also for the resource layer. Then how does it work? As I was saying, you're continuously monitoring the patient. In this case, as you see, initially we have deployed the blue service, the basic service, the mobile network, and the server that is continuously monitoring the vital signs of this patient, right? In this case, the setup is administrative domain 1, which has 3 POPs. So VIM1, VIM2, and VIM6 are the POPs, the open stacks that control these POPs. And then we have a packet switched optical network on top of a multi-layer optical network, which consists of a packet switch network on top of an optical network, and then a wireless backhaul domain here, which in this case was using millimeter wave. And then we have the growth stack, okay, or the transformer stack in this case. So in this case, this part was deployed in CTTC in Castelldefels, so in Barcelona, and this POP here was deployed in Phitonic in Madrid. Okay, and then we had a second domain deployed in Phitonic, also with 2 POPs, where since it is at the edge, because the user was in Madrid, let's say the emergency was happening in Madrid, we were interested in deploying at the edge this second service that I was explaining before. Notice also that the domain at CTTC was running OSM, and the domain at Phitonic was running Cloudify. Okay, so we are having federation between two domains that have core Mano platforms that are different. And this is the path of the, let's say, the vertical service traffic, let's say, is going this way, all the way through these VNFs, through the network in this way, the way they were placed by the placement algorithm, and they reach the server. When there is a heart attack, for example, the vital signs are altered, and then we trigger the deployment of this edge service that, as you see, we have the yellow service deployed in 5-tonic at the edge, as we were mentioning, and is automatically configured through this interface, and by exchanging the resource-related information, the service-related information that I was explaining. So it's deployed at the edge, and then the path, the new path of the information for the emergency team, so the ambulance that is reaching the spot, is this one. And as you see, it goes directly to the edge, which is closer, so we have lower latency and so on. And what you see in the pictures below are, for example, the goggles, the augmented reality goggles that are worn by the doctor that allow him to reach the exact spot of the emergency in the place of the building where the emergency happened. It also may download to the edge like some health records and so on. And these are pictures of the drill that we did to demonstrate this. Again, service creation time, not explaining the detail. As you see, the yellow part is the biggest share, is again about resource handling. So most of the issues that we have here, but again, we are in the order of hundreds of seconds, okay, for a complex service like the one you saw. So what's next? As we were saying, we are discussing how to enable all sort of stakeholders to interact in a smooth way, not just at the technical level, but also more at the administrative level. So how providers are discovered and so on, and how I select one provider and not another. So we should put some intelligence in this selection. And in terms of dynamicity and trust, we are exploring DLTs together with University Carlos III. They already have some papers on that, and we are now putting it in practice on top of this federation architecture that I just showed. There are other issues that can be handled, like dynamic service composition, so selecting what parts of the service you're interested in, what parts you want to split a composite service, and what parts go to what provider. So these kind of things go in the direction of offering the flexibility that new services will require. And then let me finish with this example of dynamic SLA management that we're integrating. So what we have in this figure is the Phi growth management platform is here. So it's the stack that I was showing in previous slides is compressed here in this case. So you could have AI/ML models running in any of the layers for the decision-making processes that you want. For example, vertical slicer, the arbitration decisions I was talking before, the service orchestrator for placement, for SLA management, for scaling, which in fact is what I'm explaining next. At the resource layer for anomaly detection and handling. So the other thing that you see in this slide is how we map the data, the typical data engineering pipeline to our architecture. So what you see is that we are gathering data from our Phi growth infrastructure, be it physical or virtual. So this is layer 0, so the event data streaming. We stream this data real time to our monitoring platform. Then we automatically generate the Kafka topics that are related to every single decision-making process that we have for this specific service. And then there are two things to be done. So the IAML platform will take this data and use it to create the models, the IAML models for this problem. And in fact, once you have this model trained with the data and so on, you download it and you start with the real-time data that you stream, you start taking decisions in any of the entities of the 5 growth management platform, right? So as you see, there is the layer 0 event data streaming, data ingestion in the Kafka, where we aggregate all the monitoring metrics that we need for taking decisions. And then we analyze the accuracy of the model and so on. So this will depend on the kind of AML policy that you use. And then eventually, when we deploy the service, we also deploy the model that is executed in this entity, and we take decisions. For example, changing the instantiation level when there is an increase of virtual CPU. And this is what we tested. And for this work, we last week we got the best fast track paper award in IEEE and EVSDN. So we are really happy for that. So what we are doing in this case is a similar infrastructure, the one you see as in the previous slides. And what we are deploying in this case is this structure of network service. What we want to do, as I was mentioning, is to monitor, to automatically configure the service when we deploy it to monitor the virtual CPU consumption, in this case of this cache server. And when the model decides that we need to switch to a new instantiation level because the quality that users will receive will not be good enough, then we scale out and we trigger the deployment of a new VM. And this is what we did in this demo, basically by exploiting AAML models. And again, these are the measurements that we did, where basically, so they are separated in instantiation, runtime, termination, as you see. You have the orders of magnitude there, but basically what you can observe is that at most it is around 1 second, the biggest component. So it means basically that compared, at least at service creation time, compared to the hundreds of seconds that you have for other components, particularly the resource-related ones, these, let's say, it's somehow much smaller. And the component that in general takes more time is the interaction with the Kafka bus to handle the monitoring metrics, right? So these are kind of the highlights of this work. Then in terms of this work, so together with our colleagues at Polito and many other, we are also working on sort of offering AI/ML as a service. So in fact, Polito is developing now this platform, and we are somehow downloading the models automatically, requesting models for a given specific problem, for a given service that we are deploying. But let's say in terms of what next, in general, the models are quite targeted towards a specific problem that you want to solve, and then making generic models and enabling generic interactions that are useful for any sort of generic problem that you may have, that this may be difficult. So there's some work to be done there. And then, of course, having a smooth integration between this AML platform and the rest of the components, particularly monitoring platforms and the data engineering pipeline. This is something that we are dealing with currently, also by taking a look at what organizations like ORAN is doing and trying to align. Then, just to sum up, so it's clear that future networks are really complex, diverse. We want a single infrastructure that is shared by all these complex services, but this single infrastructure may not belong to a single owner. So it will certainly be multi-stakeholder, multi-technology. This concept of MPN and PN is expected to become really fundamental, particularly for industrial use cases, at least. as we're testing it in Phi growth. So it's really a challenging environment, but we believe, or we try to design our Mano stack, our management stack, in a modularized way to clearly separate the functionality of each of the components so that it can scale and serve the need not just of 5G networks, but also of whatever comes afterwards. And we believe that this may be somehow a solid and tangible ground for what comes next. At least this was our intention. So what could come afterwards? Of course, everything that we explained must be revisited. So all these what's next slices that I was explaining during the presentation must be revisited to consider all these let's say, stringent requirements that Alain and Ömer were explaining before. So these much higher data rates, this much higher densification, cell-less architectures, much higher technological diversity, these new coverage areas, and of course, energy efficiency. So all these that we are doing must be revisited again, because when you put systems into stress and you move them to scale, for sure, you will have to redesign things. But at least we think we have a solid basis for evolving in this direction. And finally, let me, if you're interested in what we are doing, please go to our website where you have all public information about the project, publications, deliverables, LinkedIn. We are on YouTube also for the demos. We also have nice videos of the pilots, as I was mentioning, and more will come. You can also follow us on Twitter and Instagram. But also, most importantly, if you want to try all these things that we did, we have a GitHub account. So you can see and check all these features that I was explaining, because they are all open source. And with this, I think I'm done. Thanks.
Thank you very much, Josep, for the presentation. Let's see if we have any questions. We have some questions. While people maybe write questions for this specific presentation, there are some questions already for Alain and for Ömer. So maybe we can take those also, and then do this like a kind of closing panel Q&A session. So there is a question from C to Alain. She basically asked if the roadmap that you presented towards 5G, until 2030, are a common view for the different SDOs, 3GPP, ETSI, etc. So Alain?
Yeah. Well, that's an interesting question, actually. So as you know, as you appreciate, I mean, each SDO is very much occupied with the specification of their next releases, right? So they don't have as such like a 6G roadmap yet that is agreed, for example, by 3GPP or by IEEE or IETF. But indeed, actually, what we did in this exercise in this Empower project to come up with this roadmap is to go and study all materials available to us, surrounding these SDOs like the 3GPP, the IEEE, mostly for the short term. And we tried actually to expand upon this through some extrapolation of what's coming up next, of course, helped by the emerging technology from the research community to be able to come up with this roadmap. So essentially, the SDO's input is very much around the short-term enabling technology, right? And the medium-term to long-term is an extrapolation from this, helped by the scientific research on 6G.
Okay,
I think the other question was about from Shi about the mesh network and cell-free. So I think that there would be several, let's say, technology directions that that can support such extension. On one hand, we talk about this integrated access backhaul in the optimization. Josep also mentioned between the access and backhaul and so on. So one extension would be, like we have dual connectivity in 5G. We would go more into the direction of multi-connectivity. And the dual connectivity in 5G is more like on the interfrequency dual connectivity. I think if you want to have the truly mesh networks and exploit the multi-connectivity, it should be also on the interfrequency side. And this would, on one hand, enable us more resiliency, like in the sense that like user can connect to the network to multiple routes, and then this can be also used to enhance, let's say, the capacity. That is okay, like one direction. On the other hand, if you think about like cell-free mechanisms, so today how it works is like the user moves from one cell to the other cell. It can be like moving from one DU to another DU. So what we do, basically, the context of the user is moved from one cell to the other cell, and then this can actually introduce some maybe signaling overhead and then latency and so on. So basically, user moves from one cell to the other cell. So if we can do like, then we have like fixed anchor points in the network, like some central entity, and this small cells that's distributed into the network, like maybe an extension of the IAB nodes. So they don't keep the context of the user, and then basically with the multi-connectivity, whenever user moves in the network, you just maybe new links are established, but the anchor points stay in one, let's say, edge cloud or a central entity. So basically, the network will follow the user, and then we will reduce this signaling overhead and some protocol extensions, let's say, that we can have. Of course, other things that, when we talk about sub-networks, like some specialized networks at the edge, and this would be relevant, I would say, that when we can improve the connectivity between the devices, like in industrial IoT, like some sub-network on the robots themselves, or like some swarm of drones that, like with the connectivity between each node can be enhanced, like with high reliability and low latency, I would say. Yeah. Thank you.
Thank you, Ömer. So we have another question that, well, maybe any of you can take it. That is, besides adding capabilities, 4G and 5G are also about simplification of protocols and architecture. Will the future architectures help further breaking down complexity?
Well, I mean, I can take that one if you want. I mean, as Ömer was explaining, this trend towards hyper-specialized slices and so on is supposed to be customized to the specific needs of a very specific service. So the idea is that you just deploy what you need to handle this kind of super specialized service. Then at the same time, you need sort of meta infrastructure, if you want, that allows you to deploy these hyper specialized slices, right? So then from the point of view, the important thing in terms of complexity is that the verticals, let's say the end user of these kind of platforms, perceive it as a simple thing, and they can focus on what they need. And then a different thing, of course, the complexity will not disappear in the sense that if you are increasing the number of technologies that you put on the network because you want to serve different requirements and different verticals that have their special needs and so on, indoor, outdoor, sky, and so on, I mean, the complexity will be there. You will have to handle that. But the important thing in the end is if you manage to simplify this complexity to the user. And this is what we are aiming at doing, let's say, not just our project, but many other projects. So in some sense, the answer to this question is yes, from the point of view of the end user of these platforms. But in some other sense, like it's a fact that future networks will be more complex, and that's why we're introducing EIML-based systems that would simplify our management, but the complexity will be somehow there.
Okay, thank you very much.
Yeah, maybe on top of what Josep mentioned, I mean, of course, like this, I think I also said, like, So we have some aims like to support different verticals, or even like how we observe in the 5G, right? So we on one hand, of course, we simplified that, like we reduced maybe the number of functions that handle certain functionalities into a smaller number of functions, or we introduced, like, for instance, service-based architecture principles in the core network. But of course, we also introduced, like, to support network requirements from the multiple verticals, we introduced network slicing, right? So to cover not only the service requirements, but also network requirements like the isolation or maybe specific functions to be introduced and so on. But then that means, of course, we have this flexibility of designing logical networks, but then the complexity may be moved from the network domain to the management side, how we can tackle such kind of, let's say, multitudes of the slices. So I mean, of course, there are like simplifications, or maybe some complexity is taken from a certain domain to move to another level on one hand. And then of course, like with the unification of the approaches that we apply to different network domains, I think can help further simplifications. Like, now we are going deeper in network virtualization and ready access network, so that the findings from the core network of how we handle the virtual network functions in the similar sense, the scaling up, scaling down can be also applied to the radio. So in such sense, I think this unification of the approaches we apply to different domains can be considered as kind of simplification as well. Yeah. Thanks.
Thank you, Ömer. Thank you very much. So unless you have any other point to make now, there have been a couple of questions about when the presentation will be made available. We will discuss that with MDPI, with the organizers. But otherwise, in any case, I think we will be able to put the PDF version of the slides on the project website, so that will become available soon. And with that, just a final reminder, please, if you can share your thoughts on the webinar on the link I put I shared before, and I put also on the chat. That would be very much appreciated. That will help us organizing future events and improving how to do it. And with that, I would like to thank everybody for joining, and especially thank our speakers for being here. And thank you very much, guys, and talk to you soon.
Okay, thank you, Carlos.
Thanks.
Thanks, everybody.
Thank you very much for joining.
Bye. Have a nice evening.
Bye.
Bye.
Thank you very much.